Hi, I am Ricardo Caldas, and on behalf of my colleagues, I will be presenting our paper accepted in the Artifacts track of SIMS 2021. Our paper is entitled Body Sensor Network, a Self-Adaptive System Exemplar in the Healthcare Domain. In this video, I will explain our exemplar in 3 steps. First, I will contextualize the usage of the BSN within an intensive care unit example, and this will be used to illustrate some of our adaptation scenarios. Then, I will build on each of the individual components that form the BSN exemplar. Last, I'll glimpse over the process for executing the BSN exemplar. We model the BSN as follows. The patient is modeled as a component that provides vital signs such as heartbeat rate, temperature, blood oxygenation, and so on. The sensors are modeled as components that collect these vital signs from the patients, filter them, and then send to the central hub. And the central hub processes the collected data and triggers doctors or nurses when a patient is in an emergency situation. As discussed before, in the intensive care unit, the BSN may face several uncertainty scenarios. For example, an expected number of users, uncertain sensor sampling rate, and uncertain sensors availability. The unexpected number of users might happen in situations where the healthcare system is facing an unpredicted demand. In this scenario, the number of vital signs providers, or the patients, increase, and so the number of sensors collecting the vital signs. If the central hub is not prepared for this demand, the emergency detection might be slowed down or even crash, which is unacceptable for a safety-critical system. Another type of uncertainty is the uncertain sampling rates. This scenario can emerge when distinct patient profiles or unexpected diseases are affecting the patients. This demands that more or less data is collected in a fixed time period. The sampling rates affect the sensor's emergency consumption and may lead into a scenario where a sensor runs out of battery. Once one or more sensors runs out of battery or fails for some other reason, the results of the emergency evaluation may be compromised. This characterizes an uncertainty sensor's availability. Therefore, we have implemented a component called uncertainty injector that lets us simulate all these uncertainty scenarios and even more. The uncertainty injector can induce failures by generating noises in the format of a step, a ramp, random, and impulse signals. These signals can be parameterized by amplitude, frequency, offset, or even an intensity, and they can affect each of the components of the application. The noise injection affects the reliability of the system. We capture this information by monitoring the logs generated during the application execution. In the number of user scenario, for example, we show that by increasing the number of users, the system fails to deliver correctly the service. And this is reflected in the reliability of the BSN, as you can see in the graph to the right, under these red markings. To tackle such disruptions, we provide a system manager that acts by adjusting the sensor sampling rate, restoring the normal reliability level when a disruption is detected, as you can see in the red markings. The system manager was implemented by 2 components that select a coping strategy and enacts this strategy using a PID controller. For more information, please check our paper published and presented in the SIMS of last year. To summarize, we offer a file-based custom patient component for generating vital signs, 6 customizable sensors for collecting vital signs data and a central hub, an uncertainty injector with capability of disturbing the system using 4 types of curves, with which we could illustrate the simulation of 3 uncertainty scenarios and can be extended for many more. A reusable and extensible control theory-based managing system, and logs from which reliability and cost curves can be plotted after the execution. All of these components were implemented in ROS using C++, and Python can also be used. Okay, how can we use the BSN? First thing you need to do is to go on our GitHub page, github.com/lesunb/bsn. There, you will see that you have 2 options. First, you can use our virtual machine for people in a hurry. This will take around 10 minutes if you have all the prerequisites in your computer already. Or you can follow our detailed instructions to build, execute, and analyze the BSN. For that, we highly recommend that you watch our demonstration video posted on YouTube. Thanks for your attention, and for more information and further discussions, don't hesitate on contacting us.